Hello, Sauce here. This is a pre-calculus lesson. We're going to talk about rate of change from data. I have a table that I'm starting here. We're going to imagine the context of a rocket taking off. And we're going to complete this table with some data which will show the height of a rocket after seconds after it has taken off. So the first point that we would put in here naturally is at time zero, or the initial time at the very beginning, the height we could imagine is 0. That's the rocket sitting on the launching pad. And if we had a stopwatch and we read the height of the rocket 3 seconds after it took off, we could imagine that it would rise maybe 70 feet. I'm going to put a couple of more data points in here. After 9 seconds, we'll imagine the rocket is at 701 feet in the air, and 21 seconds after launch, the rocket is at 4,533. This is data, the context, and it has a context, height after time, or height as a function of time. I'm going to graph the situation to get a visual. Typically, we put time on the horizontal axis whenever time is involved in data or a contextual situation, and we're going to compare that with height, labeling the vertical axis. How do I label my tick marks? Well, it's usually wise, if I'm going to fit the graph in, to put a tick mark on the vertical axis at the highest point, or approximately the highest point that the data reaches, and on the horizontal axis I'm going to put a 21 here. And all of the other important tick marks then would be relative to those maximums. So if I've got 4,000 here, I'm going to approximate this tick mark to be 2,000, which makes 700 around there. And time, I'm estimating this is about 10, so I'm going to put 9 and 3. So it's a sketch. It's not precise, but it'll give us a visualization. Plotting these points, the point 0, 0 is at the origin. After 3 seconds, we have just a little bit of height. After 9 seconds, 701. And after 21 seconds, we are over the 4,500 mark, approximately there. So this is a few data points. We could imagine, we don't have data for this, but we could imagine that connecting these points with a curve would fill in the table, part of the table that we don't have, and we could imagine that this is a graph of the height of a rocket as a function of time. Now let's talk a little bit more about this context and how it relates to a rate of change. We can make a ratio out of the change in the rocket's height and the change in the time. We can make a ratio where the numerator, change in height, and the denominator is change in time. Why would we do this? Well, let's visualize the situation a little bit. What does it mean to have a ratio change in height divided by change in time? Visualize a rocket that is starting on the ground and is rising. And if you're comparing the rise to how long it takes to get to any point in its rise, then what you're measuring by comparing those is the speed or the velocity of the rocket. This ratio, change in height over change in time, is the concept of velocity. If the rocket changes by a great height in a short amount of time, then we would say that the rocket is moving fast, has a high velocity. If the change in height is very small, when the change in time is long, then that would be a slow velocity. The rocket is rising at a slow rate. Velocity is a rate of change. How do we calculate that? Change in height, we have a symbol, delta, and we can abbreviate height with an H. Delta H is a symbolic way to represent change in height. And of course, delta T would be the symbolic way to represent change in time. Delta H over delta T is the velocity of this rocket. And we can calculate a specific velocity by choosing heights and times, making ratio with numbers, and calculating velocity. We're going to do that. We're going to calculate the average velocity from, and we have to pick a couple of data points, from t is equal to 0 to 9. This calculation is going to come from calculating the ratio change in height, how much the rocket moves up, divided by the change in time, how long it takes to move up. Now with these specific numbers, the change in height we can read from the table. A finishing height at time 0 is 701, and if we subtract the initial height at time 0, then we'll get the total amount of change from 0 to 9. Same thing with time. If we take the time at 9, and that's easy because time is the variable that we're comparing this to, so from time to go from 0 to 9, the change would be 0 minus 9, and that simplifies quite nicely. We have a 701 divided by 9. That's a velocity. It's going to make a little more sense if we approximate it with a decimal. 701 divided by 9, a calculator will show you that that is 77.889, rounded to the nearest thousandth, which is a good habit to be in when you have to approximate decimals that continue forever. And because this is a contextual problem, the units are important. This is feet per second. The velocity of the rocket from time 0 to 9 is 77.889 feet per second. That's how fast the rocket is traveling, on average. So at any point in between 0 and 9, the rocket is moving at a different speed. But on average, along this interval of time, the rocket is moving about 78 feet per second. Now this delta H over delta T, this calculation hopefully looks familiar. This right here is a slope calculation. Rise over run, or the change in the vertical information divided by the change in the horizontal information, is the slope calculation. This is the slope of the line between the 2 points that we selected. Again, this is a slope calculation, and the 77.889 is the slope of the line between the 2 points that we selected for this average velocity. Velocity is a slope. Let's compare that to another average velocity calculation. We're going to calculate the average velocity, and I'm going to use interval notation this time. Average velocity on 3 to 21. This is interval notation for the time, 3 to 21. And we know that this is going to be a slope calculation, rise over run, but in this case the rise is not y, it's h for the context of height, and the run is not x, it's change in time, because time is the horizontal variable in this context. To find the change in height from 3 to 21, we take the height at the ladder value, which is 4,533. To calculate the change in time, we still have to subtract we have to finish the change in height, we take the latter value, 4,533, and we subtract the beginning value, 70. The change in time from 3 to 21 might be a little simpler to calculate, but we'll show the work as 21 minus 3. We're going to take these differences, simplify our fraction. 4,463 divided by 18. And we'll go for a decimal approximation. Calculator will show us that this is 247.944 approximately. It's been rounded to the nearest thousandth. And the units, because this is a contextual problem, feet per second. This is faster. It's a higher number. The average velocity on this interval is greater than the average velocity on the previous interval. Quite a bit greater. 247 or almost 248 feet per second. Look to our graph. If this is a slope, this velocity is the slope of a line, what line? In this case, it's the slope of the line between 3 and 21. If we drew a line that connected the 2 points that we used, the line that connects this location and this location, which we used in this calculation, then is the slope of this line is the velocity of the rocket on average between those 2 points. The higher velocity of this line is seen in it having a greater slope. These two lines, because they connect 2 points, are called secant lines. A secant line is a line that intersects in two locations. The slope of this secant line is the velocity, on average, between the 2 points that it intersects the graph. And velocity is a rate of change.